It's my pleasure to introduce our next speaker, Dr. Jim Miller. Jim has designed and implemented many novel and useful systems, ranging from the first full-function email system to the first portable implementation of Scheme. Most recently, Jim has been working on the Common Language Runtime at Microsoft. Please join me in giving a warm welcome to Dr. Jim Miller.
I want to thank you, and thank you for staying, and thank you very much for inviting me here. I've really enjoyed this conference. This has been just tremendous fun. Meeting all of you and listening to talks has been really exciting. This particular one brings me back about 6 years. I was the first person to give a talk about .NET publicly, and I did it in a huge auditorium, much bigger than this, 10,000 people. And the speaker trainer, said to me, "There's only one thing worse than speaking in a 10,000-person auditorium." I said, "What's that?" He says, "Speaking in a 10,000-person auditorium when there are only 5,000 people there, because it looks empty." This is what I got. And that was also right after Bill Gates, so it sort of feels the same way. It's like, by the way, there's a comment in there somewhere about two college, well, one was a dropout, one never went on and hasn't yet gone on to his academic work, and here I've got my PhD, and you can draw your own conclusions. Anyway, all the faculty have gone away, so it's safe to talk about this stuff. I want to talk about something that's not really my specialty, but something I've just been fascinated with, and the title of this conference, I decided would be really one of the most appropriate talks I could give, because I'm going to do a lot of reflecting on what's happened in computer science over the last 50 years or so, and just a little bit of projecting forward. So this is mostly my work, but I want to give credit to a real good friend of mine, Carol. Where is she? Carol Light, there she is, who works on she now works at Microsoft. It's very funny. When I started this talk, she was at Hewlett-Packard. She was the first woman fellow of Hewlett-Packard Corporation, and then they had a big round of layoffs, and she took early retirement and came into Microsoft, so she's now at Microsoft. So what I'm going to tell you about is, first of all, I assume almost everybody here must know what a compiler is. Is there anybody who does not know what a compiler is? Okay, but just quickly about that, I'm actually curious, who here is not an undergraduate student? Whoa. Right, that surprised me. That's more than half of you. Okay. So what are you? Graduate students? A bunch of graduate students? Former students? I don't know what to say. For people out in the real world or out in academia, I guess that's the real question. How many of you are really working? Okay. And how many are just teaching? Ooh. I used to be a teacher. I'm allowed to say that I was on the faculty at Brandeis University for a number of years. Okay, so we'll talk about what is a compiler, just so we have some common terminology that I'll use throughout. And then I want to give you a brief description of the history of developer tools. So the division of Microsoft I'm in is primarily about developer tools. And then I'll tell you, everybody's got a first compiler, and I'll tell you about my first compiler. And then I'm going to tell you about where compiler technology has gone and why that technology is interesting to study, even if you aren't interested in compilers. But I'm curious, how many have already taken a compilers class? Okay, so most of you. Right. It'd be interesting to compare it to what you learned in those classes. So what is a compiler? Well, it's a converter from one representation, which we call the source code, into another, which we call the executable code. And the job of the compiler, the best I could come up with to describe it, is it preserves most of the meaning of the source code. There are some things it doesn't preserve. We'll talk about that too. And the other thing is it's one part of a modern tool chain that's used to produce executable artifacts, which we call applications. So those are the two things that really are what a compiler is. And here's, if you open up the compiler, what's it look like on the inside? Well, all right, take source code in, which describes the behavior. Compiler, executable code out, has your desired behavior. The interesting thing is that this executable code may have a very different structure from your original source. So your source may be in a functional form that doesn't say anything about order of operations, and this one has all sorts of information about the order. And we'll talk about why that's important as we go through. Now, the interesting thing on sort of the historical part of this talk is there are three figures of merit, three ways. If I ask you what makes the best compiler, I give you two C++ compilers, and I ask you which one of these is better. There are really three very distinct ways of measuring and answering that question, and they're all valid. And to me, it's sort of the 50-year sweep that we're talking about. You're going to see a change in the way people think about this. So one measure is code quality. How efficient is the code that's generated by my compiler? And there are really two metrics there, too. That really is speed and space. How fast does the code run, and how much memory does the code take? And that used to be important. These days, it turns out those are not really independent. And if you want things to go fast, they can't take much space. So you really need to do the same thing in both cases. But there's a second metric, completely different, has nothing to do with how good the output code is. It's how fast does your compiler run? And for certain applications, that's a more important concern than how good the code that it produces is, which seems a little odd, but we'll talk about that. That's one of the major trends, I think, over the last 50 years. And then there's another one which most people don't even think about, but just like there's a time-space trade-off in the speed of the output of the compiler, there's a time-space trade-off in the compiler itself. So sometimes the issue is not how fast does your compiler run, but how much memory does it take in order to run. So that's what I call the footprint measure. Okay, so now we'll talk about how did developer tools develop themselves. So it starts in the 1950s. I was not in the computer field at that time. I wasn't even born at the beginning of this era. So just for some historical perspective. In these days, we were just lucky to have a compiler. This is when the compiler was invented. Compilers were built referencing a runtime that was needed to run the code that they generated. But the runtime was really part of the operating system. It was placed in a given place in memory. It never moved. And the kinds of runtime systems I'm talking about are like the Fortran runtime system, which is the input-output format statements. Fortran is the first programming language I actually learned, and almost half the time I spent learning it was devoted to the one statement, the format statement. If you've ever studied Fortran 4, you'll know what I'm talking about. That's the runtime library for Fortran. There's also the math part, but the math is just swamped by the size of the input-output library. And the COBOL runtime, which dates from almost the same era, I think they're about a year apart, which took the I/O stuff and added to it searching and sorting. So that's what's in your big runtime libraries. Now the operating system is sort of part of the tool chain here, and it loads the compiler output into memory and transfers control to it. So all really that your loader does is it sort of grabs the bits the compiler generated, puts them in the right place in memory, and jumps into the middle of it, and it goes. And the address space is small on these machines. 8,000, that is not a typo, that is a K, not an M. 5,000 words of memory. And the CPUs are slow by today's standards. They're 1,000 instructions per second. So think about that. Think about writing a compiler that can live inside of those constraints. And what's the figure of merit on your compiler? Well, the first figure of merit is could you get one at all? The first Fortran compiler I used, which I used in the 70s, the very early 70s, or actually it was the late 60s, so a good 15 years after this, was in 52 passes. And you had to load 52 parts of the compiler in order to compile. In order to fit, each part had to fit in that 8,000 word limit. So that's the sort of technology you're dealing with there. So the only interesting figure of merit was code quality. The compiler had to optimize your code for space and had to optimize it for speed, or it just wouldn't fit on the machine. And what did the compiler look like? Well, this isn't how you would have described it in those days. This is what we look at, sort of look back on it and say it's divided like this. There's the compiler, the source code comes in, it goes into a front end, that goes into the output to a back end, and then you have executable code. And the front end's job is to parse that source code. It produces an abstract syntax tree, AST, and it produces a symbol table. And then it also is responsible for generating all the interesting error messages. So syntax errors, type errors, unbound references, all that sort of stuff. That's all on the front end of the compiler. The back end of the compiler takes that parse tree that was produced by the front end, linearizes it usually, does some code analysis on it, and figures out where the basic blocks are, and does control flow and data flow graphs. It does machine-independent optimizations like removing redundant code and removing dead code, restructures the code in various ways, and then it converts it to executable code and does machine-dependent stuff there. So it figures out what goes into which registers. It looks at small sequences of code together and says, OK, I see that's 6 instructions. I could do that better with 2 instructions. That's peephole optimization. It does branch prediction and tensioning and all that sort of stuff and produces the output code. And notice the back end, it's almost always a failure of the back end if it generates an error. They're not supposed to fail. All the errors come out of the front end. The back ends fail for things like I ran out of memory space or I ran out of disk space. They don't fail for other reasons. So move ahead 10 years. And it was the very end of this era is when I joined the computer field. This was when linkers are invented. And it's interesting as I'm not a historian. I play one on TV. No, I'm not a historian. I have a really good friend who's a historian, and he and I talk about this sort of stuff. It's interesting to ask the question, why did linkers or anything get invented at this point in history? And the reason that it's happening in the 60s is because we invented compilers, we were able to write more complicated programs because we had easier languages to write them in. And as a fairly natural result of that, the programs got bigger. Right? And we built the programs using libraries because we wanted reusable code, because you couldn't afford to keep rewriting the same code all the time. And you had, this is the first era in which we sort of went from people who were, in the 50s you had people whose only thing was really to work on the computer. And they were the programmers and the hardware designers and sort of all mixed, and they were the computer guys. In the 60s, you had a mix of people who needed the computer as a tool and people who worked specifically on the computer. And you got those latter guys who turned into programmers, right? They wrote these libraries of reusable code, so the guys who were actually trying to get something done, and they were the people who wrote in Fortran and COBOL and stuff, could do it without duplicating the code. So libraries are invented sort of as a social process here to get the professionals to write the reusable code, and then the guys who are doing it to get work done didn't have to do that part of the stuff. It's also when virtual memory is invented, partly because of that same problem of large programs, the memory here is unbelievably expensive. We're talking about sometimes at the beginning of the 60s, it could be priced at about $1 a bit. At the end of the 60s, it's down to a measly penny a bit. So, at that price, you couldn't put that much on the computer. And, I actually saw the women who sewed the cores together to make these memories. You couldn't make that much of it. So, so virtual memory is invented as a way to get around that problem. So with virtual memory, you can play this nasty game that I only have 8K, I might have purchased 8K of physical memory, but I want it to act as though it's 16K of memory. So I kind of, when you need the memory, I move it there, and when you don't need it, I hide it somewhere else, like off on a disk. And the tool chain is sort of in 2 stages now. You compile modules independently and produce lots of little files, and then you combine them together in a linker. That's how libraries work, because they're written separately from the main programs. And the figure of merit on the compiler hasn't changed. Well, we're more interested in the speed of the output than the size, because we've got virtual memory. We don't have to worry about size anymore. So it's really about speed. Right? And so now the world has gotten somewhat more complicated. So now your source code, several independent modules, they get put through the front end, they get put through the back end, and you get, instead of these executable code, you get these things which we now call object code. And the magic thing about these is they include external references. So this thing, which might be my main program, may have references to stuff that's applied in this library, and it's the job of the linker to put that together and make the executable code. So that's really what we've done is independently compiled things put together by the linker. Jump ahead 10 years. This is when I really entered the field professionally. I finished my undergraduate stuff. I took a few years off and went into industry and was in this industry during this period of time. And I'll self-aggrandizement or something. I invented the symbolic debugger. There had been debuggers around before, but they were all at the assembly language level. I wrote the first one for a higher level language. And this was the era when that whole idea took off. I was just lucky that I was the first one. There were a bunch of other people who were working on it simultaneously. It was just in the air. Everybody was doing it. It was also when the operating system was written in a higher level language. This is when both Multics and Unix come about in this era. And that's a really important, another on the sort of the social side of things. That's an interesting proof point. It's been 20, 25 years since the compiler was invented. It's just now that that technology matured enough that we can entrust our most valuable resource, because these computers were so expensive in these days, that compute time was more expensive than the salaries of the people using them, which may sound funny today, because how many of you have one with you, right? That is one of the tremendous revolutions that's happened. When we were doing this, the computer was several years of my salary. So, but we've entrusted that thing to these technological artifacts, these compilers, and we're running the operating system in them. In the high-level languages now, so we've moved up the food chain a little bit from Fortran and COBOL, and we've got lots with proliferated. My God, by this time there must be about 500 different programming languages and about 25 or 30 of them in very, very active use in industry. And every one of them has a different set of libraries that are convenient for the use in that particular language. And so you've got these libraries along with the compilers. And you need this static linker that we had in the last time around just to pick out the right pieces of the library. So it also subsets those libraries and just pulls in the pieces you needed. The introduction of the symbolic debugger does something interesting to the tool chain. Because previously, remember, the front end generated this symbol table, and it just kind of gets thrown away. Well, you can't do that anymore, because the symbolic debugger wants to know what are all the types, what are all the variables, tell me all those names. That's exactly what's in that symbol table. So all we do is, technology rarely makes really big leaps. So sort of the incremental leap here is to discover, got to keep that stuff I was throwing away, got to keep it around, and got to standardize its format so that debuggers know what it is, so you no longer can just, the next rev of the compiler, I change the shape of the symbol table. That game, which we've been playing successfully in the 50s and 60s, goes away. In the 70s, those things have to be put external for other tools. The tools don't change at the same time as the compilers, and so all of a sudden, symbol tables become a standard file format. They become standardized, regularized, that sort of thing. Figure of merit on the compiler hasn't changed. It's still about the speed of its output code. And the system has changed a little bit. As I said, we take that symbol table that comes out of the front end, and it used to be just thrown away, and we put it out for the use of the debugger. 1980s, most of you are busy being born. Is that true? Were you born in the 80s? My goodness, I hope so. This is the era when two major. I'm cheating. I'll tell you right now that I'm cheating. The dynamic loading was not invented in the 80s. Does anybody happen to know when dynamic loading was invented? Roughly, just a guess. It's actually in the 60s. The Multics operating system, which I mentioned, was the precursor to. The joke used to be that Multics is many of whatever 10x is 10 of and whatever Unix is 1 of. The Multics operating system, and that's actually the origin of the Unix name, by the way. It actually derives from Multics. Multics was a dynamic loaded system. And the whole idea of dynamic loading sort of died with Multics. It required hardware support. It was slow as molasses. And even Multics had to reinvent static linking in order to actually get useful product out the door. And then in the 80s, the technology had turned around and suddenly became worthwhile. And for those of you who've heard the two previous entrepreneurship talks that I heard here, I will add one other piece of advice if you're looking for your next great thing that you're going to do and take off. My friend, who's the historian, says that computer science is the only field in which he can reliably predict the next breakthrough. And the reason is that it is what was the research idea 20 years ago, but the hardware wouldn't support it. And this is an instance of that 20-year cycle. The dynamic loading invented in the 60s, hits in the 80s. You can think about it. So start looking now, pull out those books, what was hot in 1986. Right? And the other thing that's invented in this era is threading. So this is sort of a complicated piece of the history. We want to improve the operating system performance now. And the way we have to do that is by reducing the pressure on the physical memory. Physical memory prices have dropped to the point where it really isn't all that expensive, but you still can't have an infinite amount of it. And the programs have been growing and growing and growing because it's easier and easier to write them. And we have symbolic debuggers, so we could actually debug them now. And all that good technology, programs get bigger. And so we really want to be able to take this library code, which we're sharing between all the applications, and we'd really like only one copy of it in the physical memory so that we can reduce the memory pressure at the operating system level. And so we moved to this system where instead of loading the whole system in at once, we incrementally load the pieces, and that's why you have dynamic loading, and that's why we share this code. Now, the operating system now, remember, we've had this loader since the 60s, but what it used to do was just grab all the bits, put them in memory, and jump to the starting point. Now, with dynamic loading, it's the thing that has to connect all the references from code that was compiled to the actual thing that got loaded. It's not the linker that does that, it's the operating system loader. So all the work that the linker had to do, the operating system has to do again. And so we just took all that wonderful linker technology that we had in this separate thing, and we run it once to do static linking, and then we put it in the operating system and run it a second time to do dynamic linking. So that's the dynamic loading story. On the threading story, concurrency is like really hot now, in case you haven't noticed it. That's another, we're talking 20 years, right? Okay, so 20 years ago, concurrency became important, and threading was the way that was invented to deal with it. But there isn't any really good direct support for it in programming languages back then or now, in my opinion. It is, however, when the idea started coming around. So people invented the notion of locks and monitors in events and polling in the 80s. Ada, which was invented in the 80s, one of the interesting, unique design features that was done in Ada was one of the few successful language techniques for dealing with parallelism that I've seen to date, which is the rendezvous, and they did a nice job of it. My PhD thesis did another one in the 90s, but the one in the 80s definitely precedes it. Concurrency has a really obnoxious problem. It used to be that we had one thread, and so the compiler, remember, its job is to do meaning-preserving transformations from the source to the object. Well, if the only thing that can happen is you've got this one thread, the compiler can rearrange anything, and as long as nobody can see what it did, then it can make those rearrangements. So there's a whole bunch of optimizations that are feasible, that all of a sudden, if you've got two threads running at once, and they're running in the same virtual address space, so they can see the same bits of memory, then all of a sudden there are optimizations that you can't make, because while when there was only one guy, you didn't notice that I was loading this variable early or setting this variable early. That was perfectly reasonable, and it sped the program up to set it early. Unfortunately, this other guy might be looking at that variable, and you just don't know. And in a world in which the threads are not part of the single program, but they're dynamically loaded in with you, you can't even know whether somebody's looking at that. So you have to do much more complicated analysis in the compiler to prove that nobody else could see the variable. Or you have to decide that you're not going to make those optimizations because someone could peek. Or you don't bother to be careful, and you just assume that people won't peek, and you hope that nobody peeks, right? And people have pursued all three of those approaches, right? And it's all a question of what you mean by meaning preserving in your program, and people can argue about this for hours or months, or if they're academics, for years in journals, right? And the tool chain has changed. Okay, so the tool chain now is compilers, linkers, the loader suddenly is in there, and the symbolic debugger. This is also, for a whole bunch of reasons that are really complicated, have to do with hardware architecture and differences in speeds and stuff. This is the era in which it's finally really recognized by almost everybody that if you're worried about code quality, speed and space are not independent anymore. With virtual memory in the picture, it had already become the case that really space and speed were almost the same thing, and now it's become just eminently clear that caches are beginning to appear on machines here. If you don't fit in the cache, then it's 100 to 1,000 times slower than if you do fit in the cache. That means you better fit in the cache if you want high speed. All those kinds of things start coming up now. So here's our world now. The tool chain just gets more complicated, right? Through the whole time. It is not going to simplify. Okay, so now, remember we have this object code coming here. These could reference each other. And you run it through a static linker to resolve all those references. So that still happens. But then you dynamically load things, and guess what? They reference one another too. So in the OS, you repeat that stuff. Right? So that's what happens here. 1990s. Garbage collection hits the mainstream. Now, this is an idea that goes way back, too. It was in Lisp and APL and Smalltalk, but those were really not mainstream languages. They date back to the, well, Lisp goes back a goodly ways, and the others go back into the 70s. In the 90s, Java hit major big wave there, and JScript and C# and Visual Basic all have garbage collection built into them. And I'm not going to give the arguments about why it's good or bad or whatever, but the garbage collector hits in here. Verification. We start worrying about computer security here. That's, I'm not talking about, there's all sorts of other stuff going on, right? So networks are coming in here, and the web has already hit. So that's why we're suddenly worried about security. And what we want to do is be able to independently have people who we don't really trust write programs and run them in the same address space as the code I'm writing without having it cause my program to fail. And we rely on type safety, so that the reason he can't write to any of my memory that I didn't want is because he has certain data types that only do certain things, and I have to prove that he's abiding by the rules of those data types, and that's what verification is about. Now, verification, the technology of verification is very much like what front end of a compiler does anyway, and so we wind up building into runtime this notion of verification, which is kind of like the compiler, what it's doing. And in order to speed up languages like Java, which initially started out interpreted, it's a great idea that we should, take that code and put it into an intermediate language in the compiler, and then compile it when you need it. So you don't compile it all at once, you just compile it in little batches, and your compiler doesn't take very long because it's not much code, and that's actually much better than interpreting it. Generally, even if you're a bad compiler writer, the output of a bad compiler will run at least 15 times faster than the interpreted version of it will, and a decent compiler gets usually a factor of 40, so it's worthwhile doing that. So now things get much more complicated. So the way we deal with this is you sort of split your compiler in two. You have that front end that does the syntax, generates all the errors. That's all the users care about. Remember, backends never had errors anyway. So the front end is the only thing you care about. So that's what you call your compiler. And remember, what was the output of that front end? It produced an AST, the syntax tree, that went to the back end to compile, and a symbol table that went off to the debugger. And the great idea that comes in the 90s is let's just stop it right there. Let's just call that the compiler. And those two output things, let's put those into the output file of the compiler and do all the rest at runtime. I'm going to show you the picture of it in just a second, but let me tell you what's happening here. Is this part? I'm just curious. Have you seen this part of how these virtual machines work nowadays with JIT compilers? It's stuff you're basically familiar with. All right, so it's not. So the fundamental thing that suddenly happened here was we moved the compiler into the runtime. The back end of the compiler is now part of the runtime, right? So here's what the world looked like in the previous slide. And we're going to just take one vertical slice of that. All right? That's what our tool chain was like if you were just worried about one source file previously. Now when we throw a JIT compiler into it, here's what happens. We take the source code, we put it through the front end, and take we take the image file out here and give that to the OS loader. So we don't go through the back end of the object code anymore. We just give that to the loader. By the way, we put the symbol table in this file too. So it's the AST and the symbol table. We take the AST and linearize it, and we call that an intermediate language. So it's byte codes, or it's IL code, or whatever you want to call it. But that's what we put in this file. That's what the OS loader loads. Then after loading it, while it's running, we dynamically link it with other pieces of code. And as that code references pieces that have not been used before, we run them through the back end of the compiler and then run that program. So at no point do you have the whole program ready to run, usually. You only have the bits that you need. But now, this back end is happening while you're running the program. So all of a sudden, what's the metric on it? All of a sudden, the runtime of your program is dependent on not the code quality of this, but the throughput of this and the code quality of this. And guess what? The throughput in almost every application, the throughput of that thing is deeply tied to how good its code quality is. The better the code quality, the worse its throughput. And most people won't tolerate, in an interactive application, the kinds of times it would take if you want high optimization out of that. If you want good code quality out of that, you've got to trade it off for throughput. And that's the big thing that happens and changes the world right there. Okay. So that brings us up to now. And this is the only place where I'm projecting instead of reflecting. And I'm going to project by reflecting. This is the era of reflection-based computing. I didn't pick the name of this conference. It's just a wonderful pun. Thank you, whoever did it. Okay. There's lots of other stuff going on in this decade. I mean, another thing is parallel computing has suddenly hit big. But the reflection-based computing has suddenly hit big also. And that makes a big difference in this tool chain at all. So what's reflection? That's the ability, while the program is running, for it to look at its own stuff. What types does it have? What variables does it have? Looking at them, changing them, creating instances of them at runtime when the person who wrote the program didn't know the name of the type that was about to be instantiated. So you, the programmer, don't even know the name of the data type that's going to be created in these instructions. It's only known at runtime. Now, for many of us, like I come from the Lisp community, from the Scheme community. This was a yawn. Of course, we've been doing this since 1960s, right? But it's a big deal now, right? It's also now the case that the interactive development environments have suddenly become really, really important, really popular, and they make programming for the masses unbelievably easy. And they do it by using things like what Microsoft calls IntelliSense. That's the ability to, you type in part of a name of a variable, and it tells you what all the possible completions are given where you are in the program. So it knows about the syntax of the program, and it knows about the symbol table and all that kind of good stuff. All the refactoring of things. Interactive syntax analysis, so you can highlight and color the program. All of that sort of stuff is basically based not quite on reflection, but something very similar to it. Another thing that's going on right now that's causing a lot of buzz, and that the reason I don't do like much projecting when I do my talks these days is that I'm an optimist. So in the 90s, I was giving talks, or in the 80s, I was giving talks saying that the 90s was when we were going to integrate query languages into real programming languages. And it's just beginning to happen now. It's really happening now. So I'm delighted to say that that prediction, while a bit late, is happening. And in order to do that kind of query that integrating queries into the programming language, you have to build an abstract syntax tree of the query at compile time and shove it off to the query processor at runtime so it can optimize and actually generate the code to do the query. So all that stuff is coming together right about now. And the figures of merit on compilers are really wacky. And it's really hard to understand what to do. And if you're a vendor like Microsoft, which makes compilers amongst many other things, for each compiler, we have to figure out what's the important figure of merit and how much do you invest for one use versus another. And those become major economic decisions. So, for example, do we have one C compiler, C++ compiler for the operating system, and a separate one for customers to compile their own code? This would make an awful lot of sense in a lot of ways. The operating system has demands on a compiler that are just not made by any other program ever. But it costs an awful lot of money to maintain two compilers and for exactly the same language. And then if you find bugs in one, you need to fix them in the other, or you completely fork them and they're independent, and then features you put in one don't appear in the other. And customers don't care about those things, but customers want you to do other things that they care about that the operating system would just as soon you didn't do. And so that kind of economic decision is really very difficult. And Microsoft's decision was to keep those as one compiler, and so figure of merit becomes a real issue on the C++ compiler. For the operating system, what does the operating system care about? Do they care about the throughput of the compiler? You've got to be kidding, right? They're going to sit there. How long does it take us to build Vista, the final build of the Vista operating system, just to compile and link and prepare the bits to go out? Does anyone want to make a guess? 24 hours, I heard. What else? 3 days? I don't know the actual number, but the last time I checked, it was over 10 days. Okay? And that's not on one machine, trust me. I don't know how many machines either, but it's a large number of them. Okay? Now, operating system in Microsoft is sort of a weird concept. It includes a whole bunch of stuff that no rational being would call part of the operating system. But that thing you get in the box that's called Vista takes over 10 days and on a large number of computers. So do they care about throughput of the compiler or not? Some parts of the operating system care and some parts of the operating system don't. Right? The deep kernel guys who are involved in the lowest level absolutely got to have the highest qualities. Does MMC, the snap-in thing for managing the computer, it's a GUI app, for heaven's sake. Of course they don't care about that. Right? So, all right. And then my team, which deals mainly with the managed programming languages like the Java and C# and Visual Basic, we care deeply about the JIT and its throughput, but we also provide an option for people who don't want to have that, to have a back-end compiler that runs in advance of running the program, and there we change the figure of merit. So this is sort of where we end up. So that's sort of the tour of languages, of the history of the developer chain. Now, this is my timeout. I just like to talk about the very first compiler. I didn't write this. This is the one that I studied the internals of. You have to understand that when I was in high school in the late 60s, I was very lucky to be able to use a computer at all. And they had these magic things called compilers, and I tried like crazy to find out how they could work. They seemed absolutely magical to me. I couldn't imagine how it was possible to do what they did. And I finally went out and spent probably all the money I'd earned in my life to buy this little teeny tiny book that was for graduate students on compilers. And it was the Fortran assembly program. And it was the compiler for the Fortran language. And I got it and discovered it was only an assembly language listing in a machine language that I had no idea what it was, with no comments. So it was a bad investment. So I got a job as a programmer, however, with this absolutely nutty guy. He was a genius. He's actually one of the founders of the ACM. And he made his first million selling a book in 1948 called Giant Brains, or the Machines That Think, which was about computers. And in the 70s, he wrote, I think it was the 70s, he wrote another bestseller called Mathematics for the Intelligent Non-Mathematician, which, if you can still get a copy, it's worth getting and reading. It teaches you how to approximate, which almost nobody teaches, and which is a life-saving skill. But anyway, he published a magazine, and it was called Computers and Automation. And in it, there was a column called Numbles, Numble Puzzles for Nimble Minds. And it had these little things like send plus more equals money, and every one of those letters has a numerical value, and your job is to figure out what numerical values will make that thing into a true mathematical equation. And I was the editor of the Numbles column. So my job was to, every month, take out Bartlett's Book of Familiar Quotations, pick a few quotations, type them into this program, which would then go and tell me whether there were no solutions, one solution, or many solutions. And I would pick one of the ones that had only one solution and make that month's puzzle. And I went up to Ed, and I mentioned Ed Berkeley, and mentioned him that I was really dying to find out how compilers work. And he says to me, well, that program you're using, that's a compiler. Hey, what do you mean it's a compiler? Yeah, well, what it does is it takes this thing you type in. So the input language is send plus more equals money, right? And the output language is a program that puts every possible number in for every one of those letters. And then it runs the program, and it tells you the values. And it was a hand-coded PDP-9 assembly program. So that was my first compiler, and I just thought that was really neat. And that's one of the, by the way, that's one place, that's what, one of the things that triggered me about the fact that compiler technology isn't just in compilers. I never thought of that program as a compiler. Nobody in their right mind would. And it really wasn't a compiler. It was a compile and run thing. So it compiled this program and then it ran it. And that's what disguised it. And so this section of the talk is really about that idea that another thing that's happened sort of concurrent to what I've been talking about is compiler technology has been moving into other places that you don't think of as compilers. So it moves into other places in the tool chain. It moves into other places of mainline technology. And I want to talk about that. And I sort of identified sort of 5 kinds of places where you find compilers these days. So obviously compilers themselves, but then hidden underneath the hood of other things, inside of applications, some places in the tool chain, and inside of code libraries. So let me talk about some special purpose compilers. There are compilers that compile the hardware. One of the ones that I worked on in the, I think it must have been the early 80s, was a scheme compiler. So this was an interesting project. Actually, Guy Steele did this at MIT. He was leaving just as I was arriving there. What they did was they wrote a program which took scheme programs and compiled them down to an intermediate language, which they could then take and combine with a library that described VLSI chip designs and transform scheme programs into chips. And so there's only one interesting scheme program from Jerry Sussman's point of view that has ever been written, which is the scheme interpreter. And so you take the scheme interpreter and you put into that, and what comes out is a piece of silicon that runs scheme programs natively, and that was called the scheme chip. So, but that idea has been done in other languages in other ways, and that's one place where compiler technology has moved. And if you're in the hardware end, and the EE end of this field, then you do use these kinds of technologies, and so this compiled hardware is an idea we're still using. Aspect-oriented programming, which has come and was really big, and people are telling me it's dying and good riddance, and other people are telling me it's coming back again, but whatever. That's another place where compilers are hidden. These things called the Weaver is nothing but a compiler by another name. You take the program out, you put in some code, put it back together in the weaving process, and you compile it. Another place that's kind of interesting is all of these workflow and object design languages. We have things which we're now giving to the business guys, the guys who are not programmers, to simply drag and drop pictures of work, pieces of work that have to happen, and then you draw little flowcharts showing how to compile how those things work together, and out pops a program that does that. That's a compiler with an unusual input language. The input language is visual, but other than that, it's just normal compiler technology. There are markup compilers. There's compilers for anything that starts with an X. Every time you get another X thing, it's got a compiler with it. So we have XML schemas or DTDs, which are their predecessors. So we have compilers for these things. Their input is those things, is a schema, and their output is maybe a parser, or their output is a deserializer, or their output is both. One goes to the client, one goes to the server. Right? That's all compiler technology in there. WSDL, Web Service Description Language, same idea. You get these proxies generated for you automatically. That's just compiler technology. XAML, the stuff that's in this new Windows presentation framework, it's all the same trick. You have a compiler that generates a parser on one side and generates a thing to execute it on the other side. I mean, it's a great idea. I mean, how many times do you want to see it, though? Right? Okay. How about inside things? Inside of the CPU, right? Modern chips don't execute the instruction sets that they have. That was a big revelation to me when I sat down and discovered this. The CPU architecture is a complete abstraction these days, and most chips actually take the thing you think of as your programming language and compile that down on the fly to something that their hardware can actually execute. And they don't tell you what it is, and they change it generation to generation, and all they do is keep that interface stable. So actually on the silicon there is this, what amounts to a compiler. I mean, the whole point is to allow the hardware world to innovate without affecting the software world. And that notion, which you can trace back to the virtual machine back in the 1950s, it's a recurring theme, and it's a great theme. How about in the graphics world? You have these graphics chips. A new trend that I found out the last time I gave this talk is that the people who build those chips are now starting to say, hey, we've actually got an interesting engine for doing normal computing here. Why don't you compile to us? So there's a trend going on in that direction. But independent of that, when you write graphics programs these days, you tend to write them in terms of things that are useful for the design of the graphics. So you tend to talk about pixels and pixel shading and surfaces and so forth. Well, that ain't what the hardware handles. The hardware handles typically triangles or rectangles, and the steps that convert from the description you gave to what actually the hardware can do are generally hidden behind an abstraction barrier, so you don't even see it. And in fact, I had an interesting conversation with one of the major vendors in this area, where they said that the thing that they keep proprietary, two things about their chip. The hardware guys care deeply about some of the details of the actual hardware design, so obviously that's kept secret. The software guys, everybody knows there's a compiler in there. Everybody knows what the source language is. Everybody knows what all the optimizations are. The thing that they keep secret is the order in which they do those optimizations, not in terms of do I do this optimization before that one, but at what stage of the pipeline do they do those? Because it makes a big difference. What's the one thing you want out of your graphics card? High throughput. Right? What's the last thing that means you want to do in your graphics pipeline? Compile a program. Right? That's going to kill your throughput. So that means that they don't want to do it while they're doing the operations, but they got to do it sometime. And so exactly when it's done is an interesting trade secret, and it differs from vendor to vendor. How about inside of other applications? One of the most interesting ones is inside of SQL, the database language. It's a full programming language. The way it typically works is you compile it to some intermediate form on the client. In the bad old days, which are still going on, that's done by actually typing the query in a string and then running the compiler actually in the client to generate this intermediate form. In the good days to come, I hope, we've integrated the query language into the programming language. So you have put your query in line in your programming language. You've got syntax checking and all that analysis done then, and it builds the intermediate form. And then that gets shipped off to a back-end processor. So that's the first compiler. Right? But that's not the one I was talking about here. Because the actual interesting compilation is what happens when it hits the server. Because there you have this query optimization story, which is its own compiler that starts with that input form. And it differs from the traditional compiler because it's got a bunch of additional input. So it knows things like this query is going to reference these tables in the database. So it knows the size of those tables. It knows the frequency of various kinds of queries because it's been watching them on the fly going past and it's gathering statistics. And it knows what indexing information it has on those tables. So with all of that stuff, it does a traditional type compiler analysis and produces as output the executable code. Obviously, you've got to do that. But also, it may build some temporary indices to speed up this particular query. It also may say, I've seen enough of this kind of query that it's worth producing this kind of index information in the background. So it starts that process off for the benefit of future queries that come in. And it updates the frequency information of the various kinds of queries so that it can continue that process. So it's one of the more sophisticated uses of compilation technology. It's also used in hardware. Compilation is also used in hardware emulators. All the newer computers are coming out. The software doesn't get rewritten for them. You have to reuse the old software. And it used to be that we would write an emulator by just writing in my new computer language an emulator for the old thing. That's the interpreter strategy. That's not how anybody does it anymore. About 10 years ago, maybe 15 now, it became evident that, gee, if I compiled it instead of interpreted it, it would run even faster. And now the question is, do you compile the whole thing or do you do it in pieces? And people have tried both approaches. So you've got JIT compilers and you've got non-JIT compilers, and they're both used in that kind of hardware emulation world. That technology is just plain all over the place. It also turns out to be very interesting to use emulators of the same machine. Those are virtual PCs is one thing they're used for, but another thing they're used for is debugging scenarios where you want to be able to do things like step backwards through your program execution. Well, you can do that if you've got one of these good compiled emulations of your own hardware. And people do that trick, and it's fascinating. And I think that's one we're going to see more of that. We're going to see more and more of these hardware emulators just to make the debugging and design process better. You'll also see it in all sorts of code analysis tools. So all of this is sort of restructuring technology, remodularizing implementations is really just a compiler under the hood. It's doing standard front-end analysis of the syntax of your program, discovering where all the references are. And you want to rename something, it knows all the references are so it can rename it. Or you want to move this chunk of code over there, it knows all those standard front-end, back-end, standard abstract syntax tree analysis. It's all compiler technology, all of that sort of stuff. Tree shakers. These are, remember when we first introduced the linker, we said that one of the things it does is it takes this large library and pulls out only the pieces that are needed for the program that it's actually trying to build. Take that technology, apply it to the abstract syntax tree, you get exactly the same thing. They're called tree shakers. And they package up the pieces that you need, throw away the stuff you don't, and collapse the program. How about inside the tool chain itself, inside the IDE? This is it's a place I happen to know because it's what my team does a lot of work on. The code editor. All of these modern interactive environments have a code editor that knows the syntax of your programming language. And they're all, well, almost all. Java's the only holdout. The Java environments really only know Java. Most of the other ones know lots of programming languages, and they're extensible. And basically, they have the front end of the compiler built in to the editor so that it can warn you about syntax errors and it can do coloring. The project system, the thing that actually handles tracking all the files that you want to put together to build, does a similar thing. It wants to know if I'm editing this source file, it may be referencing stuff in that file, so when I compile that one, I update all the references over here, and we have a cooperative front end. The front ends of the compilers talk to one another. And by the way, those things might be in different programming languages, so you have to have some language-neutral representation of that stuff. The build system, it's a little bit less about the compiler. I mean, it mostly just launches the compiler. Debuggers have pieces of the compiler in there because almost every good debugger these days, back to the old symbolic debuggers, has an expression evaluator where you can type in an expression in your favorite programming language and it will produce the value. Well, what is that? That's at least the front end of the compiler doing the syntax analysis, and then it's either interpreting your thing or actually generating code on the fly. So it's either a compiler or an interpreter, but it certainly has the front end of the compiler built into the debugger. It's a place you might or might not expect. How about things like what Microsoft calls edit and continue, and what Lisp systems and APL systems have had for ages? You're typing along in a workspace, you make changes to your program, you get a bug. When you get the breakpoint or a bug, you don't restart the program, you edit the program text and continue it. What language do you edit it in? You edit it in your source language, of course. Guess what? There's a compiler again. So that damn compiler technology, it just shows up everywhere, right? I think we talked about both of those. In the linker, who would have thought inside the linker? That's after all the compilation happens. Well, the compiler, the linker is one of the few things that sees the whole program, whatever that means, because in dynamically linked systems it doesn't, but let's leave that aside. So inside of the linker, there's very commonly now a piece of the compiler that takes the object format of the system, that's its input language. It does standard flow analysis like the back end of the compiler, but now across multiple compilation units, and so it can optimize across multiple programs, and there are large sets of optimizations you can get at that way. The problem with this is these flow graphs are huge, and so in fact that's where we get to this question of whether you really care about throughput or not. This is the first time actually in all these compiler technologies where the footprint of the compiler becomes the gating issue. We tried to use this technology at one point to build a subset of the operating system, just the kernel. And the flow graph for the kernel essentially spans more virtual memory than you can fit. You can certainly fit, it doesn't fit in a 32-bit address space, forget that. It would probably fit a 64-bit address space, but the amount of virtual memory you need is quite large, and you can't back it with enough physical memory to be useful, so you can't really do the whole flow graph. So you have to back off the optimizations in order to get just the space needed to hold the data structures to describe the program to fit in any reasonably useful amount of memory. I'll skip on and get to the end here and then see if there are any questions. So inside of programming libraries, there are interesting little compilers. So almost every good programming library these days has a regular expression parser. So you can look at a string and tell me, does it start with an A and end with a B, and I don't care how many letters there are in the middle, right? That kind of expression. That's a compiler in most cases. The input language is the regular expression language, and the output language is either some little thing to interpret for matching or actually a program to do the interpretation. So it's kind of interesting. Serialization and deserialization, which in the web, and especially in Web 2.0, everything you do is about taking your data, putting it on the wire for somebody else to read, and having them read it back. Well, how does that stuff work? Well, when you serialize it out, if you're using a dynamic language to generate it, then you don't know in advance what the data structure is going to be, despite the fact that people may think it's all schema-based. It generally isn't. It's based on the instances of data, and there's usually additional data being passed. And you wind up discovering that, you know what, at runtime, you need at least the analysis pieces, at least the reflection pieces of the system in order to be able to serialize and deserialize data. So reflection sort of got built down into that web access stack in odd ways. And for the compiler writer, for years we've had sort of standard libraries for compiler writers, Lex and Yak being the granddaddies of them. Abstract syntax tree toolkits. Microsoft has a bunch of these that we're playing with. Some we're rolling out in preview form. Some we're probably going to ship in product. Some we're using internally. Executable file formats. You can go out on the web, and for almost any computer, you can find out toolkits for building and reading and writing executable files. And then the one that I think is kind of fun right now from my point of view is this project we've got called Phoenix, which is producing a research compiler toolkit that we're putting out on an open source license for people to play with, where it's just written as sort of, it's written the way every compiler should have been written, including ours. So it's modular, and the optimizations are modularized out, and you can try experiments like, if I do this optimization first, is it better than doing this one? And what happens if I limit the size of these data structures versus those data structures? And so there's a whole toolkit for playing around with that, for back end only. So that's been sort of a quick tour through where that compiler technology has been and where we're going, and be glad to open up for questions about this or other Microsoft-related questions. Yeah. Ah.
Okay, the edit and continue functionality in Visual Studio 2005 has really saved my butt under some really tight deadlines in the past year, and every time I hear anyone talk about it, they say it's black magic, it's voodoo. How exactly does it work? Or is that just? Or I have to take a college course on this because it's too complicated.
Don't try to write it on your own, let me tell you that. It took one of our best developers 2 entire cycles. In fact, a brief story here, edit and continue, which I think is really one of the really nice features that we have, is actually a feature that belongs actually on my team, the Common Language Runtime. There's some surface stuff that's done in the higher levels, but almost all of it's actually in the virtual machine engine. And it was planned for the first release of the Common Language Runtime. We spent 5 years doing that first release, and the hardest cut we had to make at the end of the cycle was we cut, edit, and continue, because despite all of the effort we put in that 5-year period, we couldn't get it to work. However, what you do in that, this is back to that entrepreneurial, you try it, you fail, you get up and you try it again. In the next cycle, which was only a 1.5-year cycle, we actually made it work. The reason is we learned all the things you can't do. It's what's left is what you do. And the way it works is you have to have built your whole engine so that you have the notion of deltas to the existing code, and you have to build deep into the runtime engine the notion that there are patch levels for the code, and you have to have the ability to intercept any method and say, I was about to call that thing, hijack it so that instead of that, it goes off to some central routine to figure out what the highest patch version of that is, because someone's patched it, and it may or may not be visible to you, which is a weird off thing in the way our system works, is that because the same code could be executing in different domains, you may be editing it in one but not the other, so it has to at runtime figure out whether this is the one that needs to be fixed. And so it's extremely expensive. I mean, you do not want to run your program in production in this mode, because you don't take any performance measurements in this mode, but for debugging time it's absolutely great. But the way it's doing it is hijacking method calls, hijacking all the field references, and a long series. This is actually what differed from our first version to our second version, was we sat down at the beginning of the second version and very carefully went through a list of every conceivable edit from a technical point of view that can be made, and for every single one of them, he said, would it be possible for us to recover from that? And if the answer was no, we went back to each of the programming languages and said, okay, your syntax editor must detect this case and warn the user that that edit cannot be made. Our runtime then rechecks to make sure that they're not there. But in the first version, the editors hadn't been checking, so the runtime was seeing these edits that were illegal and popping up, illegal edit things, and the user was just getting this. They'd do something that seemed like a perfectly safe edit to them. Since the IDE wasn't prepared for that, they actually went through, did the edit, everything seemed fine, they'd press go, and then all of a sudden this edit that made 10 minutes ago would fail, and it was a horrible user experience. So just bubbling it back so the editor detects it and warns you, rather than the running of the program warns you, turned out to be one of the big turning points.
You mentioned about putting queries into the compiled code. And I wondered if you could highlight in a little more detail how that's different from what we're doing today and what the future could look like if we did that.
Boy, I would love to. There's an entire talk. It's public. There's actually a public download you can get from Microsoft called LINQ, L-I-N-Q. It's a language integrated query. We are basically, we're adding to the syntax of both C# and Visual Basic standard type SQL queries. You can say select, X from blah blah blah, where this, sorted by that, as syntax of the programming language. Because previously that was fine for the query processor, but if you're in the programming language, you put that as a string in your program in double quotes, and then at runtime it would hit the string, and the back end would tell you that was an illegal query. Now it's strongly typed, it's checked as your program is run, as your program is edited, and you get all the usual strong support for it. So that's what I mean by integrating into the language. And it's done in a very elegant way, because the changes to the syntax turn out to be relatively small, because there's a programming library which we're making open to the public so that other languages can adopt it, which basically you take your language, you produce a syntax tree using this library, and then the implementation of that syntax tree is the stuff that does the checking, and then that can go back to the back end and get turned into queries and so forth. So it's really worth looking into. LINQ is the name of the project, and there are several different versions of it coming out.
You mentioned link time optimization and how it's too expensive to use for the full operating system. I know that GCC and some other Unix side projects have been considering integrating something like that, and I was wondering if you all have integrated it for use in smaller things than the full kernel. Seems like for languages with heavy runtimes, it could be pretty beneficial.
Oh, we have it. It's available. It's been in the product actually for a while, and you can turn it on. It's just you have to be aware of what the cost to you are going to be. So yeah, it's a fully supported. I think it came out in the last release of Visual Studio as part of the standard linker.
Two more questions.
I have a question about obfuscating source code, because I've noticed that in Java and C# and other just-in-time compiled languages that people have been able to make some pretty impressive decompilers. So where do you think obfuscation of source code is going to fit in, and at what level in that diagram you had?
Well, the problem isn't obfuscation of the source, it's obfuscation of the binary. There have been two things that we've investigated. We've investigated leveraging digital rights management technology, and I'll just tell you, I personally find that entire thing just revolting and offensive, but that's a whole different story. For technical reasons, we rejected that, but there is an option there. And the other is to do obfuscation of the binary. And what Microsoft, we have investigated this 4 times, I think, in the past 4 years, come to the same conclusion every time, which is that there's no need for any support in the underlying system for obfuscation. Everything that is there that we can think of is available to third parties. And we've gone and actually talked to 3 different third parties to produce obfuscation softwares. And there's one that's taken it up and actually makes a commercial obfuscation package. It works extremely well. It certainly defeats the normal reverse compilation. It isn't obvious to me that it's the weird thing to me is this. There's also perfectly good, in fact extremely good decompilers for native x86 code as well. And they work almost as well. And almost nobody bothers to obfuscate their code. Now Microsoft has started obfuscating its own code in x86. And so that native stuff we don't support in managed code. But the standard obfuscation tricks work perfectly fine, and they seem to defeat all but the most determined hackers. So we've basically left it at that. Any other question down here?
So projecting forward a little more, do you see compilation moving into the cloud, as they call it?
Yes. And that's really all. Not that I can't say any more other than it seems it's the obvious next step. The interesting question is exactly how you want to do that. There's going to be a wonderful world of security issues that get opened up there. I think it's tremendously interesting. It isn't. One of the interesting things that I think we're going to see fairly soon is, well, at least I hope we're going to. I hope we're going to move away from the only language you can program the web in is JavaScript. This is not wearing my Microsoft hat here. This is back when I was at W3C before I ever got to Microsoft. JavaScript is not a well-designed language, and the security talk this afternoon was barely scratching the surface of the problems of that model. I want to see other languages, but for every other language I know of, the right way to do it is to do the compilation to an intermediate language on the server and bring the intermediate language down. So I think at least that level we'll definitely see in the cloud. Whether we will see the back-end compilation in the cloud also is interesting. Doing it in the cloud is one good way to offload the extreme expense if you want to do high optimization. You better be charging for that service for anything reasonable. And I don't know who's willing to pay for that service. So, it's a really fascinating question. I think there's no question it's going to move there. Yeah. Okay, thanks very much. I really enjoyed this.
So once again, we have the Birds of a Feather ACM meeting in 2405 at 10 o'clock tomorrow.